So welcome back to Lecture 5. Continuing on with thermodynamics, we are now going to talk about something that is called Hess's Law, which I always like to think of as a mathematical puzzle to try to get things to fit together into something that you want. And it uses this idea of our enthalpy being a state function. In other words, it doesn't really matter how we get from reactants to products, just that that's where we start and that's where we finish. So with our thermochemical reactions, remember that enthalpy of reaction is extensive, and that means that it can be affected by amounts. It turns out they are also affected by the direction that a reaction is written in. So there's a couple of different ways that we can manipulate a reaction and how we can handle trying to find values for delta H. So let's say that we have a chemical equation that gets multiplied by some factor. Maybe we have a set of stoichiometric coefficients and we want to double that for some reason. Well, if we double all of those coefficients for the reaction, then we would need to multiply the delta H by the exact same factor. In other words, if I have twice as much reactant, make twice as much product, I am also going to either make or absorb twice as much heat. So let's look at this example here. So in the first reaction, we have the reaction of sodium into water. It is exothermic. And when we have two sodiums, 2 waters, giving us 2 sodium hydroxides and an H2 gas, we get a delta H of negative 368.6 kilojoules. Now, if I cut all of that in half to where I have just 1 Na, 1 H2O, 1 sodium hydroxide, and half an H2, then I just have to cut my delta H in half as well, so that would become negative 184.3 kilojoules. If I reverse a chemical reaction, then all I do is change the sign of delta H. If it produces heat in the forward direction, then it will absorb the exact same amount of heat going in the reverse direction. So if we look at the combustion of hydrogen gas, so 2H2 plus O2 going to 2H2O, that has a delta H of reaction of negative 483.7 kilojoules. If I flip that reaction, now I have 2H2O going to 2H2 plus O2. That is now an endothermic reaction with the exact same magnitude. So we have a delta H of positive 483.7. Now you may be asking yourself, why do we want to do this? Well, if we have a chemical reaction that can be expressed as the sum of a series of steps, then the delta H for the overall reaction is the sum of the delta H values for all of the steps. And this is where this idea of state function comes in, and this is what Hess's law is all about. Maybe there's a reaction that I want to know the delta H for, but I can't actually do the reaction itself. I can still find the delta H of the reaction if I can find a series of reactions that when added together will give me the reaction that I want. So here's just some examples for you to try.
Put this on the web for a series of steps and the delta H for the
So here's a problem for you to try. We've got a reaction up top, 4N2 plus O2 goes to 2N2O5. It's got an associated delta H. We've manipulated it somehow, and we've got a new reaction, and you need to find the new delta H. And look for that solution on the link. So again, let's look at Hess's law. We've talked about how we can handle delta H in the manipulation of thermochemical reactions. Because delta H is state functions, and this is what Hess's law is all about. So Hess's law is going to look at the summation of heats of reactions. So once again, if a chemical reaction can be written as the sum of 2 or more other reactions, then the enthalpy of the overall reaction is the sum of the steps enthalpies that I use to get my overall reaction. Let's see how that works. So let's look at enthalpy of formation for methane. So the enthalpy of formation is a very specific type of reaction as written. Anytime we have the enthalpy of formation, it means that we take our reactants in their elemental form under standard conditions, and we are going to use them to make just 1 mole of product rather. So those are the keys. Our reactants have to be in their elemental forms, and we are making 1 mole of product in its elemental form. So this reaction has carbon graphite plus 2H2 gas going to methane gas. This is a reaction that cannot occur as written. Under standard conditions, we cannot make this reaction happen. However, it's still of interest to have the enthalpy of formation for this reaction. We want to know what it is for other types of chemical manipulations. So what we can do is we can calculate the heat of reaction here by combining other reactions to get this reaction. And if we know the heats of reaction of those other reactions and we can get them to add up properly, then we can know the heat of reaction for this reaction written. So let's see what we can do here. So again, this is where we get kind of a puzzle. So here's a bunch of reactions that have various forms of, or various elements, compounds involved in our final reaction. We want to see, is there a way to add all of them up, manipulate them somehow, so that we end up with our final desired reaction. So one of the things that we notice that we have delta H's for all of those reactions. All of those reactions do occur as written, and those delta H's have been measured and tabulated, and usually at the end of a textbook. Now, if we look at how we might want to manipulate some of these, notice that that third equation has methane in it, CH4. However, it's a reactant. In the reaction that we are trying to create, CH4 was a product. So we want to get that third reaction with CH4 as a product instead of a reactant. So all I have to do is flip that reaction around and change its sign. So we get this, CO2 plus 2H2O goes to CH4 gas plus 2O2. And we get a delta H now of positive 890.4. So I've manipulated one of the reactions. Okay, now let's add up the 3 reactions and see what we get. So here are the 3 reactions with that third one flipped around from what it was. And what we see is we can handle this much like simultaneous reactions in algebra. If we have anything that exists on both the left side of the arrow and the right side of the arrow, we can cancel it out. So we see that we have an oxygen. Let me go ahead and annotate this. So we have an oxygen here as a reactant and another oxygen here as a reactant. Since they are on the same side of the arrow, they add together. So that gives me 2 oxygens as a reactant, but here I have 2 oxygens as a product. And so all of those cancel out. The next thing I notice is that I have CO2 as a product here, CO2 as a reactant here. And so the CO2s cancel out. And the next thing I notice is that I've got 2 waters as a product here, 2 waters as a reactant here. And so the only thing I'm left with is carbon and graphite, and 2H2 gases is in the reactant side. And on the product side, all I have is CH4. So when I add all of that up, I get the reaction I was looking for. C graphite plus 2H2 gas goes to CH4 gas. And notice now all I need to do is to add up all of those delta H's, and I can now get a delta H for a reaction that I cannot physically do, but I still know the delta H for it as minus 74.7. So these types of problems, as I mentioned, are a lot like puzzles. Sometimes you require some trial and error to get right. Sometimes you need to multiply a reaction to get the appropriate stoichiometry. Sometimes you need to multiply it by a whole number like 2 or 3. Sometimes you need to multiply it by a fraction like half or a third. It just depends on what's given and what you need. Sometimes you need to reverse a reaction to put something in from the reactants into the products, or vice versa. So they are kind of fun once you get the hang of them. So you might try to practice some from the textbook. But if you have any questions on any of these, please let me know.